Alrighty. So good morning, afternoon, evening, whenever you happen to be watching this. Today we're going to talk about Module 6, which was specifically related to vector multipliers and vector operators. So a lot of different things can be done with these. There are different ways to look at vectors, whether they be fields or whether they be vectors of a particle at a point, some motion. There are different ways that we can look at any sort of vector and try and distinguish some information from them. So a couple of the easier ones we could talk about is when we look at some of what's called differentiation. I've got some things I'm going to write down. We won't write all of it down by word, all right? But if we're looking at differentiation, usually what we're going to be looking at is taking some form. A good example would be maybe a position vector. We're looking at like a particle or something. We could take a position vector of something. We'll call that r of the vector of position. Usually it's going to be related to time because as time progresses, your position is going to change. We can look at a position vector, and from that position vector, we can look at the differentiation, or we could do some derivatives of this vector to try and find out some information. So if we take the derivative of a position, you'll find a velocity. And then if you take the position of a velocity, you'll find an acceleration. So some information we can do with this position vector is find out when it could be at any velocity, or also at what time it could have some form of acceleration. So we can get some general terms or some general formats here where if we look at the derivative of position, we'll find a vector that is velocity. All right, and then if we take the second derivative of that position, or you can take the derivative of velocity, either way it's the same thing, you can end up finding the acceleration vector. All right. So an example we can go through, I could just put one up here. If we wanted to find using some vector analysis, we could find out what the velocity is if we're looking at a position vector. So let's say I have a position vector. I got this one off of line. It was a really nice way to kind of encapsulate a few different pieces. So we have 3t cubed, not squared, starting off strong here, 3t cubed plus t, and that would be in the I hat, all right, which is kind of like your x, plus 5, the natural log of t. We'll make it a little interesting, encapsulate a couple different things here. J hat, which is like your y, and then 5t squared plus 3t minus 5k hat, once again, kind of like your z. So if I wanted to do the differentiation or find the derivative of this, the derivative, like we said here, the derivative of our position is going to tell us about our velocity. So if I'm looking for velocity, what I would do is I would find the derivative of each individual component with respect to t, and then I can use that to find out, adding it together, you can find the entire vector in all three I, j, and k, what it would look like for a velocity. So you can find them individually. So we can just call this the x of t, the y of t, and the z of t, because they kind of mean the same thing as the I, j, k. All right, so then all I have to do is find the derivative. So I take xt prime. All right, if I look at this, 3t cubed, all right, take the derivative, you're going to end up with 9t squared plus 1. So we get 9t squared plus 1. Y hat of t, so we're looking here. All right, we get 5. The natural log of t is going to be 1 over t. So 5 times 1 over t is going to be 5t. And then z prime of time is going to be 5t squared. The 2 is going to come down. You're going to end up with negative, because we have this negative out here, negative 10t plus 3 to the 1 over there. We get that t to the 1 gives us a 3. And then negative 5, there's no t in there, so it just goes away completely. So I end up with these three components. So the x prime, the y prime, and the z prime. So if our r of t is here, the derivative of that is going to tell us, we're going to end up with the velocity vector with respect to time is going to be 9t squared plus 1 I plus 5 over t j minus 10t plus 3k. And theoretically, you can incorporate this negative in there if you want to leave it. All right, you kind of, for terms of correct formatting, you probably want to have it out in the negative here. All right, but this then tells me what I wanted to know, which is at any given point on our position right here, this is our position vector, I can also then know what its velocity should be at that one point. So if I wanted to plug in any time, I could plug in, let's say, time after 1 second. My position, if I plugged it in up here, would tell me what my position was in the I, or the I, J, and K, or that X, Y, T. And then the same thing here, I could then also, if I plug in 1 for T, I could then learn at the exact time what my velocity would be. Okay, so when we're looking at differentiation for those vector components, it becomes really useful to find out general things like position, velocity, and acceleration. All right. Sometimes we may end up want to do vectors where we can do a couple of vectors multiplied by each other. That kind of becomes an aspect that we want to use in our vector analysis sometimes. So when we're looking at vectors, we can do these same things with dot products and cross products of vectors. They just take a little bit more utilization of the product rule. So let's say I wanted to find out with respect to time what vector A dot vector B would be. We would end up using the cross product. We would take the derivative of A times the dot product with B. So derivative of A with respect to time dotted with the original vector B plus A dot dB vector over dt. All right, this is just incorporating some of our traditional dot product rules, all right, or the chain rule. We could do the same thing with the chain rule if we were taking, let's say, a cross product of two vectors. Once again, you can be done the same way, starting with A because it is the one that is the most on the left. So that A dt, and then you'll just cross that with B plus then A cross the dB dt. Remember, when it comes to these vector, when we're doing dots and crosses, the order does matter, especially with the cross product. So make sure you're not doing these different derivatives in separate orders or crossing in separate orders, because you will get separate cross products when you're looking at those kind of vectors. So that's a little bit of just looking at the differentiation, pretty straightforward. Now we're going to move on. We're looking at if we want to find the gradient. Okay. So looking at the gradient. The gradient's really important because it tells you the direction and rate of how fast something is increasing. Okay, so if you have an R of the particle, if you're looking at it, you have its motion and something along the lines of this. I have its position, and then I have related to time. I can look at this and I may be able to tell a little bit about how it's increasing its rate of maybe its velocity at some point. But the gradient is specifically used in the way when you're looking at like fields. So vectors can tell about individual particles, but they can also give you information about fields. So when I'm looking at the gradient, we use this upside triangle right here. I'm going to do a way better one for that. We look at this upside down triangle. Looks like this. So we would say the gradient of a function. You can do this in any amount of dimensions. All right. 3 tend to be one of the more common ones. All right, but if you're looking at the gradient, which remember tells us about the kind of the rate of change or the rate of fastest increase within a field, what you would do is you would find this one's all about partial derivatives, whereas the first one was all about differentiation when we're looking at individual. So we're differentiating with respect to maybe just time or x or just y. When we're looking at the gradient, we have to do partial derivatives in all the directions. So when we're looking at gradient of a function, I'm going to choose doing it in the 3 directions. We're going to do the partial derivative of the function with respect to x, obviously then with that directional component, plus the partial of that function with respect to y. Once again, we got now j in that direction, plus the partial of that function with respect to z, then within that k direction, okay? So let's say I have a function, and this is my function of x, y, z. It should be function of x, y, z. And let's say I wanted to find the gradient at which this function right here is increasing most rapidly. So what I'm going to do then with this, I wanted to know, like we said, it is the direction and rate of fastest increase in a field. Let's make that G look more like an A. All right, so that is the definition of finding the gradient. Okay, so let's say this is the equation that we have, or a formula for our field. If I wanted to find its fastest rate of increase, all I would do is take the gradient. So the gradient, this is the operator for our gradient. Specifically, if you remove this x, so the partial with respect to x in the I, partial with respect to y in the j, partial with respect to k, and then we're going to do that partial of a specific function. So this is our function. I'm going to start then, gradient of function x, y, z, which is this right here. We would take the partial of 2x cubed y squared z over the partial of x in the I hat direction plus the partial of 2x cubed y squared z in the y in the j direction plus partial, kind of bumping in here, 2x cubed y squared z in the z direction with k. And now it's a-okay sometimes. With this one, we're going to have it where it works as a little bit of everything. But sometimes you may not have a component of the x or y or z when you're doing these gradients. So when that happens, you just take the partial derivative with respect to it, and it's going to end up being 0. Or if there's a single one, it'll just end up being a coefficient. So if we move on here, we can take that partial derivative of each one. Oops, not delta. I do a lot of delta with my other classes. So you're going to see that. I'm going to make that mistake a few times. All right, but we're looking at gradient. Partial with respect to x here is going to give us a nice 6x squared y squared z, because that x is the only thing that's being partially derivative right there. And that's going to be in the I hat. Plus, now we go to the partial of y. We have this 2y squared up here. So we're going to end up dropping that down. And we're going to end up with a plus 4x cubed y z in the j. Plus, this last one, taking it in the z, we have the z with a coefficient or an exponent of 1. So that's going to drop. The z is going to go away. You're going to end up with 2x cubed y squared k hat. Okay, so this right here would be the gradient of our original function, which would tell us its fastest increase in the field. All right, so ours was a 3-dimensional right here. So this is going to tell us in 3 dimensions what our fastest rate of increase is going to be. So that's what the gradient is used for. Now we're going to move on. And now we're going to talk about the divergence of a function, which is going to be very easy to confuse because I also made the mistake when writing it that you don't have that dot. So that divergence is actually going to be what we should have, I was writing before. So I'm going to fix my mistake. So we have the gradient of f. Now, if we're talking about the divergence, okay. So if we're looking for the divergence of something, we take that gradient times or dot product with that f, all right? So what the divergence tells us is the measure of the density of change in the strength of a vector field. So this tells us about like that highest rate of when something is changing. But specifically then, if we're looking at the divergence, it tells us the density. Let me write it out. The density of change in the strength of a vector field. So while our gradient tells us where its highest rate of change is, the divergence tells us that density of change, okay? So this is going to be that gradient dot f, all right? So when we're looking at this, we're going to actually end up doing the operator for gradient, which is that delta x, partial, not delta, partial, and then partial y, partial of z, and you're going to dot product that with the components of your function. So I'm going to call these f, g, and h, just to get things simple. We're going to stick with f, g, and h. Okay. So one of the things we can do is we can look at the divergence of a given point. We can look at that exact point, what the strength of that vector field is. So if I'm going to pick I'm going to come up with a function. So we're going to do the function with respect to x, y, z. And let's say my looks like this, x, y squared, 2, not z, 2x z, and 4 minus z squared y. And let's say we want to know what that density is at a specific point. Let's call it 1, 1, 2. Why not? So let's say this is point 1, 1, 2. All right. what we're going to do is we're going to take these components. This is going to be our F. It's going to be our G. It's going to be our H. All right. And all we're going to have to do then is use that gradient operator, but dot product it to give us the divergence. So F is going to be xy squared. G is going to be 2xz. And H is going to be 4 minus z squared y. So now all I have to do, one of the other ways we can write it is this divergence. All right, so the divergence of the function right here is equal to the partial with respect to x of only our f section now, our f function. All right, this component, not the entire piece, but only this first part. All right, once again, this also could be written as xy squared I hat plus 2xz j hat plus 4 minus z squared y k hat. But then I wanted to just separate this out into those individual components. So it could be written as either way, and this would be just how we break them up into the F, G, and H format. So we're breaking them into those three sections. So you're only taking it of F, all right? So you're going to take that partial with respect to x of Fy squared plus partial with respect to y of 2xz plus partial with respect to z of 4 minus z squared y. Okay? So now we take that to find the divergence of that given component. This is going to be partial with respect to x. This is going to stay. The x is going to go down to 1. You're going to end up with a y squared plus, right here, we're taking the partial with respect to y. 2xz does not have any y component to it, so that's just going to be a nice and easy 0. And then this last one, we have the partial with respect to z of 4 minus z squared y. So we're going to end up getting a negative, because this 4 is going to go away because it has no z component, and then negative 2zy. So negative 2zy. So our function is then that divergence of the function is going to be y squared minus 2zy. Now that is the divergence as a function. Now what I wanted to earlier, I mentioned that we wanted to look at it at a specific point. So let's say we want to look at this whole field. We want to look at a very specific point of 1, 1, 2. So 1x, 1y, and then 2 at z. So all I have to do then is plug in my information. So if I want to take the divergence of that function, all right, at 1, 1, 2, all I have to do is plug it in. Y squared right here, we got y1. So we got 1 squared minus 2. Z is going to be also 2. And then you're going to have y is 1. So then all you do is the math. You get 1 squared is 1 minus 4. You end up with a divergence, or that density of change is negative 3. The divergence at 1, 1, 2 is negative 3. Now that's not going to be everywhere, all right, because we're looking at a whole entire field, but we're looking at a specific point. But this is how you'd be able to find the divergence, or that density of change. Okay, so moving on to another important operator, we're going to look at curl. And as it specifies, curl has to do with the rotation, all right? So specifically, it looks at the tendency for a particle to rotate. You can also specify it as the rate of rotation. Now, this could be of a single particle. We could be looking at a particle. We can look at if it's rotating in one way or if it's rotating in another. All right, so either direction. It also can be done if we're looking at a field. So we can look at an entire field and garner some information about its directional rotation, if it is rotating in such a way like this. All right, we are going to specifically look at a single point to make things a little easier. And we're only going to gloss over the idea behind it. And I'm going to give an example to go along with it, but it's going to be just in terms of P, Q, R, and then the partials. I'm not going to actually go through one because it is a bit time consuming, but we are going to give the general format, which is going to work for everything. All right, it just involves using a cross product, which is then going to be a lot of work over and over again, but the same idea stands. Okay, so we can be looking at it for a particle and its rotation, or we can look at the rotation, general rotation of an entire field. Okay, so to do this, we're looking a lot at, at that gradient right here. We look at this crossed with whatever your function is of x, y, and z. So this is how you would find the curl. You would do a cross product. Now the cross product we know gets to be a little bit interesting. We'll put it that way. All right. So while it can be done with particles and vector fields, we are just going to give the general format. Okay. Once again, this right here can also be shortened to just curl. All right. So it can be the curl of f with x of y of z. Okay. We're going to do a cross product, which means you're going to have a nice matrix. So the first part of our matrix, we're looking at just those directional components. So I, j, and k. After that, your second row is going to be of the partials, partial x, partial y, partial z. And then the last part is going to be whatever section like before. If I had p of I hat plus q of j hat plus r of k hat. All right, these are going to be those individual pieces that we are going to utilize. So p, q, and r. The same way as the f, g, and h. We're just going to go with p, q, and r. Okay. Then you would do the cross product. All right. We would then cover up one section. Let's say we wanted to know in the I hat. We would remove these, and then you would take the partial of y, r, minus the partial of that z and q. All right. So the general format is going to look like this. So curl of the function. Excuse me. I've got this little erase button that tends to get in the way on my transcribing tool. So I apologize for the accidental erasures. But if we look at it, we find the curl, we do our cross product, determining all that stuff. We end up with the partial of r with respect to y minus the partial of q with respect to z. So that's our first part. That's going to be in the I direction. Minus, because whenever you do the cross product, you get that minus component. The second one. So minus partial of r with respect to x, right? Because remember, we're working on here now, so we're crossing this. So partial of r with respect to x minus the partial of p with respect to z. Plus, and that's, I apologize, that is in the j direction. Plus we're covering off here if we're going into that k hat direction, partial of q with respect to x minus that partial of p with respect to y. All right, in the k hat. Okay, so whatever function you have that ends up giving you whatever three components in the I, j, and k, all right, this would be how you'd be able to find that curl. So what this would tell you then is its general rotation. If it is a particle, it would tell you kind of what direction it's rotating. If it's in 3 dimensions, it'll give you that as well, or 2 dimensions makes it a little simpler. And then also it can work with a field, so it can give you that general rotation at any given point amongst the field. So that's what curl tells us a little bit about. Okay. And now the last one that we're going to look at is the Laplacian. So if I'm looking at the Laplacian, it doesn't seem to be as indicative off the bat on what it means. So I've got a bit of a definition for us. So the Laplacian tells us how much the value, excuse me, can't write, the value of the field differs from its average value taken over the surrounding points. Okay. So what it does is it's going to give us information on if we're looking at a very particular point in space or wherever we are on our function, it'll tell us how much different that value is from the average, not just surrounding it all, but the average surrounding that specific point. Okay. So it gets a little confusing because this is going to be the gradient dotted with that gradient of your function, okay, which can also just be written as gradient squared of your function. And it operates in a very similar way in terms of how you would calculate with the gradient. You're getting that partial over and over again. So partial f with respect to x plus partial of f with respect to y plus partial of f with respect to z. However, instead of it being this just as the gradient, it's the gradient squared. So you're doing second derivatives, partial squared of f, partial x squared, partial squared of f with respect to y squared, partial squared with respect to z squared. Okay. Once again, this is going to tell us the kind of that average, how it values over that difference. So let's assume I have a function. This one's actually really nice if we use an example. So we got a function. Let's say it's going to be x squared plus y cubed plus x y squared z. We'll just go with something simple. All right. One of the ways I like to do it, we're just going to find the partial with respect to each one individually first, and then we're going to do that a second time. But instead of doing it all as one incorporated as a giant equation, I like to find them individually and then find their second derivatives individually as well, or their second partial derivatives. So we'll just do the first one, partial of f with respect to x. If I take this entirety and I find out what that partial is, I end up with 2x plus y squared z. And then I can go all the way through and find partial with respect to y and then partial with respect to z, but I'm going to just find that second partial right next to it as well. So we're going to find that partial of f. We're just going to take that partial with respect to x a second time. So instead of taking it of here, this equation up here, or formula, we're going to take it of this one right here. So we're going to find that partial here. We got the 2x gives us an x. I'm sorry, not an x, gives us a 2. And then that y squared z does not have a second component, so we end up with just that. So that's going to be my first. Next, we're going to find the partial with respect to y. Okay, so partial with respect to y, if we look up here, gives us 3y squared plus 2xy z. Okay, remember, we're going to have to take that second partial derivative again. So after that, we're going to do it in respect to not x, but y squared. We're going to do that again. So we end up with 6y plus 2xz. So that's going to be my second component. And then once again, going back here, taking the first with respect to z now. All right. So taking it with respect to z, if it'll let me scroll up. That doesn't have a z, that doesn't have a z, that has 1. So we're going to have xy squared because that z has a single 1 up there. So that's going to go away, which means when we take the second derivative, second partial derivative, you're going to end up with 0 because we're not taking it of y. I keep messing those up. We're going to take it with z. All right. So that's going to be 0. So our Laplacian then is going to be the partial up here with respect to x squared, which is 2. So 2 plus 6y plus 2xz. That's technically one whole component. And then plus 0. So our Laplacian in total, this is that formula, is going to be 2 plus 6y plus 2xz. And once again, if you wanted to find a Laplacian at a very specific point, all right, so this is just the general formula. Now, just like we did before, let's say if I'd have a student, I'd ask them what they'd want to do. Let's go with the same thing again. Let's say, assume we like to know at that 1, 1, 2. We're looking at a different field now within that 1, 1, 2. I'm going to just plug it all in again. 2 doesn't have a component, so 2 plus 6y is 1 plus 2x is 1 and z is 2. Okay. What that would tell us is 2 plus 6 is going to be 8 plus our 4. So we end up with a Laplacian. So that difference on average at that exact point would be a value of 12. Okay. So this is by no means the end of any of these vector operators, and you can definitely get more in depth with all of this. However, this is a really good start to kind of understanding some of the major ones that we can work on. So differentiation tells us a little bit about maybe if we're looking from position, changing to velocity or acceleration. We look at the gradient, it gives us a little bit about that direction and rate of increase, specifically at the fastest point. Divergence tells us that change in the strength of a vector or field. Okay, we can look at specific points up here as well. The curl tells about kind of its rate of rotation or tendency for a specific particle or a field to be at a different or specific rotation. I can look at an individual particle, how it changes, or I can look at an entire field. Involves a nice little cross product, so I hope you like matrices. And then the Laplacian tells us about how that average differs from that surrounding point. Okay. Once again, plugging in points, always a nice thing to do. So with that said, that's a little bit about some vector operators. I hope you feel like you've learned something. All right. And that will be the end of our lesson for Module 6.